Good morning, students. Today we will discuss a very important topic related to magnetic effect of electric current. As you know, there is a one experiment performed by Oersted, and by that experiment we have understand there is a relation between current and magnetic field. Okay, and that experiment was known as Oersted's experiment. What will said in this experiment? That if there is a current flowing through a conductor, there will be a magnetic field develop around it or near the conductor, and by the help of magnetic compass needle we can detect the presence of magnetic field due to this straight current carrying conductor. So as you can see, this is the negative terminal and this is the positive terminal of the battery, and if current is flowing from A to B, there was a deflection in the needle of this magnetic compass, and that was toward the left as the experiment performed at that time. And when the polarity of this battery get reversed, then the deflection was taken at the right side. Okay, so in this way we can say when there is a current flowing through this conductor, there is a presence of magnetic field around this conductor. So now the next revolutionary experiment performed by the Faraday, and by the help of Faraday we have explore a very important phenomena that is known as electromagnetic induction. In this electromagnetic induction, several experiments has been performed to understand this phenomena. So let us see what was the experiment. Suppose this is a solenoid, or you can say there is a coil having number of turns and a galvanometer is connected with it. So if we see in this figure, if the magnet is stationary and the coil is also stationary, in this case we will see there is no deflection in the galvanometer. So next step is, when we move the magnet toward the coil, what will happen? There is a deflection in the galvanometer, and if there is a deflection in the galvanometer, it means the current must flow through this solenoid or conductor. So it means there is a distance of current when the magnet is moving toward it, but when it stops, the current will also stop. Again, the direction of this magnet get reversed, means now the magnet is moving away from the coil, and suppose the north pole is at the same place as the previous one. So again we will see there is a deflection in the galvanometer, but at this time this is in reverse, or you can say in the opposite direction. So what will happen? Again, by the relative motion between coil and magnet, there is the existence of current in the coil, and when the magnet stops, the current will also stop. And we have also performed that if the coil is moving and magnet is stationary, again there will be a deflection in the galvanometer, means there is some existence of current. So the Faraday thought that it means when there is a relative motion between coil and magnet, there is a current in the coil. So what will happen? Faraday suggests when the magnet is approaching toward the coil, there is a change in magnetic flux. And what is magnetic flux? Magnetic flux is the bundle of magnetic lines. So if approaching it toward the coil, it means magnetic flux will increasing. That means it is changing. So if there is a change in magnetic flux, there must be some induced EMF in this coil, and due to that induced EMF, there is an induced current. Okay, in a particular direction. Again, when we are moving the magnet away from the coil, there is a change in magnetic flux, but now at this time, the magnetic flux are going to decrease. So again there is a change in magnetic flux, then it means again there is a induced EMF in the coil, and because of this induced EMF, there is induced current, and due to this current, there is a deflection in the galvanometer which is in opposite direction. And when we put the magnet stationary beside this coil, there is no change in magnetic flux, so there is no induced EMF and there is no induced current. So in this way, several other experiments has been performed, and at last the conclusion was obtained that if there is a change in magnetic flux linked with the coil, there must be a induced EMF in the coil, and because of this induced EMF, there is induced current, and this phenomena is known as electromagnetic induction. So all the experiment performed by the Faraday was concluded in two laws. The Faraday's first law: when magnetic flux linked with the coil is changed and induced EMF is set up in the coil, the induced EMF lasts so long as there is a change in magnetic flux linked with the coil. This was the first law. And the second was the Faraday's second law. The magnitude of induced EMF is directly proportional to the rate of change of magnetic flux. Means, what is the rate of change of magnetic flux? If you are moving the magnet very fastly toward the coil, then the value or magnitude of the induced EMF will be high. And if you are moving the magnet toward the coil slowly, that means the rate of change is less. So you will get less EMF, and because of that you will obtain less current, and that current is known as induced current. So this means that the Faraday's second law gives the magnitude of the magnetic flux, change in magnetic flux, and hence induced EMF. So in this way we can conclude that the Faraday's first and second law define the electromagnetic induction, and third one is Lenz's law, and the Lenz's law was given to find the direction of this induced EMF or induced current. That we will discuss in next video. Okay, so I hope you could understand electromagnetic induction. This topic is basically of class 10th. So you will, if you come in class 12th, you will see the broader portion of this electromagnetic induction. So up to class 10th, you have to learn little bit about electromagnetic induction that is given in this topic. Okay, so thank you very much.